So we just introduced Markov inequality, Chebychev's inequality, and the weak law of large numbers. Let's go over a few examples for you. Okay, let me write down the question first. From past experience, I know the average midterm grade of students in my engineering statistics class is about 75. First of all, we want to find an upper bound to the probability that a random student grade will be more than 85. Very good. So let us take a look at the formulas that we have up here. We're going to use the Markov's inequality. So let us grab Markov's inequality because this is the expected value and move it down here for you guys. The probability that X is more than or equal to 85 is going to be less than or equal to the expected value, which is 75, divided by A. Remember that when you're talking about A is the threshold value that we are concerned with. In this case, A is equal to 85. So you have 75 divided by 85, which is about 88.2%. So the probability that X is more than or equals to 85 is going to be about 88.2%. Another example for you. So in this example, you have the following case. Suppose we know that the number of items produced by a factory during a week is a random variable with mean to be 500. Part A of the question. What is the probability that this week's production is at least 1,000? So in order to find the probability that x is more than equals to 1,000, we can apply the Markov's inequality. This is less than or equals to the expected value of x divided by, in this case, 1,000. This is 500 divided by 1,000, which is a half or 50%. Let's take a look at part B of the question. If the variance of these weeks, for the second part of the question, suppose the variance of a week's production is 100. What is the probability that this week's production is in between 400 and 600? So please note that since we have information about the variance, we want to apply Chebychev's inequality. Remember the formula? The probability that the absolute value of x minus mu is more than or equals to k sigma. This is less than or equals to 1 over k squared. So since we want to calculate the probability that x is in between 400 and 600, if you subtract 500, you get negative 100 and a positive 100. So absolute value of x minus 500, which was the mean, is less than 100. So basically, let me move this here so I have enough space. Basically, we are calculating the probability that the absolute value of x minus 500 is less than 100, which is not quite the same as the Chebychev's inequality. So basically, we need to find its complement. The probability that the absolute value of x minus 500 is more than or equals to 100 based on Chebychev's inequality is less than or equals to 1 over 10 to the power 2. Basically here, when you're doing the calculation for k and sigma, this is equal to 100. So k times sigma is 100. At the same time, we know sigma, which is the square root of 100, it is 10. So k times 10 is equal to 100, and k becomes 10. So that's how you get 10. To get 10 squared, basically just do the substitution. So the probability that the absolute value of x minus 500 is more than equals to 100, less than equals to 100 or 1%. So its complement, the probability that absolute value of x minus 500 is less than 100, or the probability that x is bounded between 400 and 600 is equal to 1 minus 1%, which is 99%.